So first question is one where we are considering looking at a graph of f. How do you know if it's increasing, decreasing, constant, etc.? So as you walk from left to right, if the graph is falling, we are decreasing. So we can see that the graph is decreasing here, decreasing here. So that means over the intervals from 0 to 1, it's decreasing. And for the x values, so this is 1, 2, 3, 4, 5, 6. So it looks like from 3 to 4, it's also decreasing. If the graph rises from left to right, then we are increasing. So we say that over these input values, from 1 to 3 and from 4 to 6, for those x values, we are increasing. So there's increasing and decreasing. So then where are we concave up or concave down? When we're looking at the graph of f and we're thinking about concavity, really we're thinking about U shapes are concave up and N shapes are concave down. Why is that? Because we're thinking about if I draw these little mini tangent lines, do we see that the derivatives are really big negative, and 0, and then small positive, really big positive, really big positive? So over here, the derivative is changing in a positive way, from really negative to 0 to really positive. So that means the second derivative is positive in here. In other words, we are concave up. So we're concave up in the interval from 0 to 2. Well, then it looks like we have a really big positive slope, 0, and then small negative, really big negative, really big negative. So since we go from really big positive slopes to 0 to negative, it looks like our derivatives are changing in a negative way. So we are concave down in here, and I think we're also concave down over here, you will see. So that's from 2 to, the way that I wrote it, 2 to 4, and then 4 to 6. It's also concave down. So again, in general, a U shape is concave up and an N shape is concave down. And then notice it looks like right about here is where the U shape and the N shape meet. And so that's where our point of inflection is going to be, or our point of steepest ascent up the hill. So it's where the derivative is the largest. So that would be our inflection point. All right, then down here, if we're looking at f prime, how do you think about increasing and decreasing? Well, anywhere where f prime is positive, f would be increasing, because that's what it means to be increasing. So that's going to be on this interval, and it's going to be on this interval. So anywhere where f prime is positive, or the f prime graph is above the axis, the original function f, wherever it is, would be increasing. Similarly, we know that anywhere where f prime is negative is the same thing as f is decreasing. So that means inside of here and out here, our original function would be decreasing. So from 0 to 9, from 4 to 6 and 8 to infinity, if we wanted to talk about that, right? All right. And then we look on here and we notice that if we go from increasing, because we're above the axis, to decreasing on f, so if f prime changes sign from plus to minus, then we know that that means that there is a local max at x is equal to 4, because we changed sign on the first derivative. I go from increasing to decreasing, it must have been a maximum. Right? But then over here, we go from decreasing on f to increasing on f. So if f prime changes sign from negative to positive, we know right here that that means at 6 that we have a local minimum, because we went from going down to going up. It must have been a minimum. Over here, again, we have one of those increasing to decreasing points. So right here at 8 is going to be another local maximum, because we change from increasing to decreasing on f. Cool. Well, then when we talk about concavity, we know that the second derivative positive is the same thing as concave up. So maybe I'll write that in green. So we know that where the second derivative is positive, that's the same thing as concave up. But the second derivative positive means that this thing would be changing in a positive way. So in other words, if f prime is increasing, is the same thing as, it's going to be the same thing as f double prime positive. So we see that f prime is increasing here, here, and here. So on those intervals, if f prime is changing in a positive way, then we know that f is concave up. F is concave up. F, wherever it is living, is concave up on these intervals. From 0 to 1, from 2 to 3, and from 5 to 7. Then we know that if f prime is decreasing, that would be the same thing as the change in f prime. If that's negative, so f prime decreasing is f double prime negative, would be the same thing as concave down. So it looks like we're concave down here and here and here for f, remember. So those are the intervals for which the original function f is concave down. Cool. All right. So then when we look over here, these are the ones that we said that we often see on IU finals, but just are really good questions. So if I'm given this function, let me have a conversation about increasing, decreasing. Well, there's going to be 3 steps: critical values, partitioning, and chart. And if I talk about f prime and I find my critical values, partition, and chart, I can talk about increasing, decreasing, and local mins and maxes. If instead I find the critical values of f prime, so if I talk about f double prime and I find critical values, partition, and chart, then I'm talking about concavity or inflection points. So again, if I talk about critical values with f prime, partition, and chart, I'm talking about increasing, decreasing, and local mins and maxes. If I find the critical values and use f double prime and then partition and chart, I'm talking about concavity and inflection points. So for 11, if I have this function and I want to talk about increasing, decreasing, I write out this and I take my derivative and then I say, where is it equal to 0 or undefined? Since it's a polynomial, it's defined everywhere, so there's no undefined points. When I factor that sucker, because we like factored things, find out that these are my critical values. Step 2 is to partition our interval and make 3 cuts. When I make 3 cuts, I get 4 pieces. I use that to chart. Here are the intervals that come from my partition. And up top, I use the factors of my derivative. If it's a fraction, I do any factors of the numerator and any factors of the denominator. Put it up here, because what I'm really saying is I need to know the sign of f prime, because that will tell me if f is increasing or decreasing. So I pick a number in here, maybe negative 100. 4 times negative 100 is negative. Negative 100 minus 1 is negative. And negative 100 plus 1 is negative. So that means I will have a negative times a negative times a negative at any point in this interval. And that means my derivative will be negative at any point in this interval. So that means f is decreasing. If I pick similar sorts of points in here, here, and here, I get that f prime is positive, negative, positive, which means that f is increasing, decreasing, and then increasing. So then when I look at my chart, I notice that here at the point negative 1, when I go from this interval to this interval at x is equal to negative 1, which is in between them, since I go from negative to positive, the derivative goes from negative to positive, that means I have a local minimum. And notice that that happens at negative 1 and at 1. So at negative 1 and at 1, I go from decreasing to increasing, so that means I have a local minimum. But then at one point, at x equals 0, which is in between these two intervals, I go from increasing to decreasing, so I have a local maximum. And that's the way we write it. Now, if I look at the second derivative and have a conversation, I'm talking about concavity. So I take my second derivative, find out where it's undefined in 0. When I solve, I get plus or minus root 3. Notice that plus or minus is something that's going to really come up when we take that square root, so be careful of that. I use those values to partition. 2 cuts means I have 3 intervals. And then in that chart, again, I put the entire second derivative because I worry about its sign. A number in here might be negative 1,000. Well, notice that we're always going to square it, so it's always going to be positive. And since it's really big, it's going to be a really big minus 4. It's still going to be positive. So that means my second derivative is positive. So that means I'm concave up on this interval. A great number to put in here is 0. So 0 squared, I'm going to get a negative. So that means I'm concave down in that interval. And you can fill out the rest of the chart. So notice here at negative square root of 1/3, I go from concave up to concave down. And then down here at square root of 1/3, I go from concave down to concave up. So those are points where I change concavity. So I have an inflection point, right? And that's how we write it. All right. The only thing that gets a little bit different is when we have these trig functions, the derivative just gets more interesting. So for this function, if I want to talk about increasing, decreasing, I take my derivative, and then I want to know where's this equal to 0. Well, I set it equal to 0, and now to solve this, it's more conversation than it is computation. So when I move this over, I now say, where's sine equal to cosine? Well, I remember from trig, sine is y, and cosine is x on the unit circle. So if this is my unit circle, here's a point and here's a point. Well, these are the 2 points where the x-coordinate and the y-coordinate are equal. At pi over 4, and then if my reference angle takes me down here, this is going to be negative, negative, so that's going to be 5 pi over 4, because it's 1 more than 4 pi over 4. So those are the 2 points that satisfy this equation, which satisfy this. So those are my 2 critical values that partition my interval, but notice they said you have to live between 0 and pi over 2. So when I take my interval 0 to pi over 2 and make 2 cuts, I get my 3 pieces, and these are my 3 intervals. Well, then I just look inside each interval and say cosine minus sine, what's going on there? Again, this is my x-coordinate minus my y-coordinate. So if I look over here from 0 to pi over 4, I think it's pretty clear if I take an extreme example like this, that your x-coordinate is bigger than your y-coordinate in here. So x-coordinate minus a bigger y-coordinate, since your x is bigger than your y, when you take x minus y, you're going to get a positive number in this interval. In this interval from pi over 4 to 5 pi over 4, I pick an example in here. Well, what's an obvious one? Well, maybe this one. It's pretty clear here that y is positive 1 and x is 0. So since y is always bigger than x inside of this interval, then we're going to have negative numbers inside of here. So my derivative is negative, which means f is decreasing. In here, again, I take a number between 5 pi over 4 all the way to 2 pi. We'll pick an easy example, maybe like this one. Here, x is 0 and y is negative 1. So 0 minus a negative 1 is a positive 1. So since I got a positive here, my guess is I'm going to get a positive for all of these. So that means the derivative is positive, which means f is increasing. So we really had to use our unit circle and then pick points to reason our way to these answers. So that's where f is increasing or decreasing. And then we have a local max and local min where we change sign of the derivative. Similarly, when we take the second derivative, I get this equation, which really means I need to find where sine, the negative sign, is equal to cosine. So where's x equal to negative y? So where are they the same but differ signs? Well, they have the same exact number here, and they differ in signs here and here on the unit circle. So that's 3 pi over 4 and 7 pi over 4. So those are the two values that satisfy the second derivative equation. So on 0 to 2 pi, I make those two cuts. I get my 3 intervals. And so from our picture, I pick some number between 0 and 3 pi over 4. And so a number in there between 0 and 3 pi over 4 that really helps me out is maybe this one. So when I plug in here, I get x is 0 and y is 1. So in this case, I need to be careful. It's negative sign minus cosine. So negative sign minus cosine. So here, a negative 1 minus 0, it's going to be negative in here from the picture. So I think these quadrantal angles are really helping me out here. So that's where I get my concave down. Here is 3 pi over 4 to 7 pi over 4. Again, another quadrantal angle is going to help me out. This is 0, negative 1. So if I take negative, negative 1, that's going to be positive 1 minus 0. It seems like my derivative is going to be positive in here from the picture. So that's why I get concave up. But then some number over here, well, let's think. X is really big positive, but y is really big negative. So if x is really big positive, this is going, I'm sorry, yeah, it's really big positive. This is going to be negative big, and y is really small negative. That means, ooh, I actually think that's going to be concave down. So if I look at that picture, I'm actually thinking that that's going to be concave down. So let's double check that. So if I look at this picture, if I pick something like between 7 pi over 4 and 2 pi, let's really think about this. So right here, I have an x value, which is positive, and a y value that is small negative. So if my x value is positive, then it's going to be minus big positive. And so I think this thing's actually going to be negative, which means concave down. So that means I'm going to move this one down to here. And then inflection points. So I would say that f double prime, bleep, changes sign at negative 3 pi over 4 and 7 pi over 4. So to really see that, we get negative sign minus cosine. We could go over here to double check ourselves and go negative sign. So I'm going to go negative sine x minus cosine of x. And so where does that thing change sign? Between 0, so here's 0, and so that's going to be 7 pi over 4. Yay, so there's 7 pi over 4. And there's 9 pi over 4. So all these pi over 4s are helping us out. So there's my 7 pi over 4, my 5 pi over 4, 3 pi over 4. So we see that pi's over 4 are our buddy. So let me do this picture. Boom, 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 boom. Boom. So let me take that picture and then take it over here and put it with our stuff and see if it can't help us reason our way through this with some additional help. So I'm going to copy and delete. I'm going to go back here. And let's see if we can't use the unit circle and this picture to really think through it. So if I'm in between 7 pi over 4 and 2 pi, we see that here it's 7 pi over 4. Over here we were positive, but in here we're actually going to be negative. Again, like I thought. So that is correct with our reasoning from this picture up here. This is actually going to be negative. Cool. All right. So we see how this picture really helped give us some extra support in addition to our diagram. So now you're saying on a high stakes test, would I have this? Well, no, we would really need to reason our way through here, but we definitely see that it helped. So yeah. What else do we have? Then here on 16, again, this is going to be similar to what we continue to do. So if I look at the natural log of x squared ln x, I've got my first derivative, turns out to be this function. And so where is it equal to 0? Well, either x equals 0, or when I subtract 1, I get this. When I divide by 2, I get this. And then I take e to the, and raise both sides, e to the whatever that side is. I end up getting that x is equal to e to the negative 1/2, and so those are our two critical values. But notice, because natural log is part of my function, this is only going to make sense for where 0 is positive. So if 0 is positive is what I start off with instead of the entire number line when I partition, then my only critical value is going to be here, because this is really outside of where our function even makes sense. So I'm going to have my two intervals here, and then I'm just plugging in to see if it's positive or negative. So if you plug in a positive number, well, for this is going to be positive, and for this, notice it's a really small positive number. But I know that natural log of x, if I get really close to 0, it's a really big negative number. So imagine taking a point really close to 0 in here, then it's going to be 1 plus 2 times negative really big. And so I'm really believing it's going to be negative in here. So that gives me this, which is decreasing. And then here, for this function, if I pick an x out here, well, maybe I'm thinking of an x really, really big. So that means this is going to be positive. This is going to be 1 plus 2 times. Well, the natural log of x does this. For really big values, it's very big positive. So that's where we get positive, positive, increasing. Okay. All right. And so just to kind of get you through that, we see same sort of a conversation over here for the second derivative, where we're really thinking about the fact that you can't go past 0, and we're thinking about what that function, the natural log of x, looks like. So for, again, something really close to 0 in this interval, for the natural log of x, it's going to be something really big negative times 2 plus 3. That's why it's negative. And if you go really far away from this for natural log, it's going to be really big positive. That's why we have that. Okay. And that's it for that homework. Have a great one.